Okay, and now, finalist number 10, last but not least, is Jeffrey Brock in the Department of Physics, and his advisor is Mahmud Khan, and he will be talking to us about new materials for energy-efficient refrigeration. Jeffrey.
The development of refrigeration technology was one of the many Prometheus moments of the last century. I mean, can you imagine how different our world would be today if we couldn't transport perishable goods long distances, or how uncomfortable your home might be in the summer without air conditioning? Refrigeration has worked its way into our modern lifestyle, and we really don't stop to think that much about it. But like everything, it comes with its costs. Today's air conditioners and refrigerators still rely on the same antiquated gas compression technology that was in use 50 years ago. And it puts an enormous strain on our power grid. 30% of our electricity goes to powering these devices. And how is that power created? Fossil fuels, contributing greenhouse gases to the atmosphere. The gases used in that cycle, they're also incredibly toxic, ozone-depleting greenhouse gases. So there's a lot of room for improvement here, and physics might provide a solution to that question. And what if I told you that the answer might be a magnet? Not an ordinary refrigerator magnet, but a highly specialized piece of magnetic material whose properties can be manipulated to yield a cooling effect under certain circumstances. See, what gives a magnet the attractive and repulsive behavior that we all know is a property known as the magnetic moment, which I represent on the slide here as these arrows. Now, under certain situations, these moments can align in the same direction, and then any heat particles or phonons present in the material can collide with the moments, reorient them in random directions, and in that collision process, the moments lose energy and the temperature decreases. And it's up to 40% more efficient than current technology. I'd also like to note that it can very easily be adapted to heat. We could reverse the cycle, and this has massive implications for cancer treatment, because if we were to inject these particles into someone's body and have them bind only to cancerous cells, we could heat and destroy those cells, leaving the healthy cells intact, avoiding the ravages of chemotherapy. But work needs to be done on these materials before we see them in production, and that's where my thesis research steps in. See, I investigate new materials to be used in these types of processes, and specifically I work with a class of compounds known as Heusler alloys, and they're remarkable for several reasons. First, they're completely non-toxic. Second, they're made out of so-called dirt elements, things that are cheap, abundant, and available probably in your own backyard. And third, we can manipulate their magnetic properties to maximize this cooling effect at certain temperatures. Now, what makes a good refrigerating magnet? Well, it's something that under certain situations, i.e. temperature, the moments will all align in the same direction. But the interaction between moments isn't strong enough to prevent those heat particles from reorienting them. And we've recently had some success in our lab investigating materials that exhibit this phenomenon at room temperature, which is a really important step forward for applications in commercial air conditioners and refrigerators. So while we're still several years away from seeing technologies like this available on the market, I think that my thesis research is helping provide real solutions to some of the real threats that are being posed by climate change and increased energy consumption. Thank you.